Good afternoon. Today we are going to discuss about the derivation of equal area criteria for transient stability. Before going into the topic, we need to know about the basic two terms. Those are equal area criteria and transient stability. Before going into transient stability, let us know what is stability. Stability study is the procedure for deciding the stability of a system upon some disturbances, and this is followed by several switching actions in the power system. The behavior of the power system can also have some impacts, and it may raise or lower the disturbances in the system. So, the transient stability studies is the study at which we can attain the stability even at the time of disturbances. Generally, there are two types of stabilities. The one is steady state stability and the other one is transient stability. Steady state stability is always depending on the operating conditions of the power system. Generally, the operating conditions of the power system are continuously changing, means they will be keep on changing continuously. So based on that, we have to describe the steady state stability. Whereas in transient stability, the operating conditions of the power system as well as the disturbance is a main prime factor to describe about the transient stability. The disturbances can be either mechanical or electrical disturbances. Whereas coming to the equal area criteria is a simple graphical method for concluding the transient stability of two machine systems or a single machine against an infinite bus. This equal area criteria helps us in calculating the critical angle and critical clearance angle, and this principles does not require the swing equation for determination of stability condition, but here we will be going through the swing equation. Generally, the swing equation is given as follows: m d square delta by dt square is equals to ps minus pe, whereas m is the angular momentum of the system, pe is the electrical power, and ps is the mechanical power, and delta is the load angle. Generally, this equation is almost as similar as the equations at the pendulum. Generally, when a pendulum or a rotor is in a rotating position, we need to go for the two conditions. The first condition is the speed of rotor should not be equal to the synchronous speed, and the second condition is the acceleration power should not be equals to 0. Here, PA is the acceleration power, which comes with the removal of electrical power and mechanical power. Removal of mechanical power from the electrical power. So, in order to get the main equation, we will be multiplying d delta by dt in both sides, which gives the equation as follows: m d square delta by dt square into d delta by dt, which is equals to ps into d delta by dt minus pe into d delta by dt. On taking d delta by dt common, we get d delta by dt into ps minus pe. The above equation can be written as 1 by 2 m d by dt of d delta by dt whole square is equals to ps minus pe into d delta by dt. By rearranging, multiplying by dt and integrating, we have d delta by dt whole square is equals to integration of delta naught to del 2 into ps minus pe by m d delta. So when delta naught is the torque angle at which the machine is running at synchronous speed under normal conditions. So in order to find the stability of a system, the system stability can be determined and it can be maintained stable, the transient stability. To maintain it stable, the value of d delta by dt should be equal to 0. In order to put the value of d delta by dt equals to 0, we have to consider the equation at the RHS side, that is the under root of integration of delta naught to delta 2 into Ps minus Pe by m d delta. Here we know that m is angular momentum and which is a constant, so you can take it out. And to get the stability of a system, we need integration of delta naught to delta Ps minus Pe d delta should be equals to 0, whereas Ps minus Pe gives us the accelerating power. The accelerating power means the integration of the accelerating power with respect to delta under limitations of delta naught to delta must be 0. The torque angle was not changing. As we discussed, under the above conditions, the torque angle was not changing. Also, if the system has transient stability, the machine will again operate at a synchronous speed after the disturbances. That is, d delta by dt equals to 0. So, in this criteria, our main aim is to identify the objectives to be done when a disturbance has been occurred. For example, if there is any mechanical or electrical disturbances, we find the swinging action in the machines. So, in order to eradicate those and to get the stability again, we need to make some changes in the system. Those changes can be determined by using this equal area criterion method. At first, these disturbances may be short circuit, applications of loss, or a sudden large load, or a loss of generation. The objective of this study is to find out whether load angle comes back to a steady value subsequently clearing of the disturbances. Here, nonlinear equations are solved to determine the stability. Mainly, the equal area criterion is concerned with the transient stability. It is in fact a very easy graphical method used. It is for deciding the transient stability of a single machine or another machines with an infinite bus. So, as we discussed, so let us get a recap of it. Over a losses line, the real power transmitted will be PE, electrical power. Considering a fault occurs in a synchronous machine which was operating in steady state, here the power delivered is given by PE will be equal to PM, where PE is the electrical power, PM or PS will be considered as the mechanical power. For clearing a fault, the circuit breaker, like for example, to create the stability we need to operate certain switching operations. Those operations are done with the help of circuit breakers in a power system. So to clear a fault, the circuit breaker in the faulted section should have to be opened up. This process may take 5 to 6 cycles, and the successive post-fault transient will take an additional few cycles. Post-fault transient means the transient fault that has been occurred after the switching action. The prime mover, which is given in the input power, is driven with the steam turbine for the turbine mass system. The time constant is in the order of few seconds for the electrical system. It is in milliseconds. Thus, while electrical transients takes place, the mechanical power remains stable. The transient study mainly looks into the capability of the power system to retrieve from the fault and to give stable power with a new probable load angle, means based upon the fault and disturbances occurred in the transient system, we need to change the load angle so as to attain the stability of the system, by which we can say the load angle changes are mainly required to attain stability of the system at a transient fault conditions. The transient stabilities are mainly affected by the operating conditions of the system as well as the disturbances, as we have discussed previously. Since the mechanical disturbances are very less percent, we cannot highlight them, so better going into the electrical power operating conditions of the power system. The load angles must be frequently changing so as to keep the system under stable condition whenever the faults are given. So, if we draw a graph between the load angle and the time, the unstable graph will be taking a straight line, whereas the stable graph will be taking curves. This shows that the unstable graph is showing the instability of the system, whereas the stable graph is describing the stability of the system after changing the load angle delta. Stability of the system is given with d delta by dt is equals to 0 at some time, whereas instability of the system is given with d delta by dt greater than 0 for a long time. Not all the disturbances are going to create instability in the system, but we can generally consider the long disturbances. Long disturbances are if any disturbances are occurring for a long time, then we are going to consider only those disturbances and try to reduce the instability of a system and make it to a stability condition. The instability of a system is given with d del by dt, d delta by dt is greater than 0. Whenever the graph between power and the load curve is driven, we can see the critical clearing angle. The critical clearing angle and the clearing angle are obtained from the equal area criteria graphs. The power angle curve is considered the power angle curve is considered in a graph. Imagine a system delivering the IM power of an angle del naught is working in a steady state. When a fault occurs, the circuit breakers open and the real power is decreased to 0, but the PM will be stable, as a result accelerating power. The accelerating power is obtained by the subtraction of mechanical power to the electrical power. At the time of occurrence of the fault, the machine will start to accelerate. When the fault is cleared, it will continue to increase speed before it reaches to its peak value. So at that particular point, we will be finding d delta by dt is equals to 0. So the area of accelerating is integration of d delta naught to delta c Pm minus Pe d delta is equals to 0, the area of accelerating. The area of deceleration is given by dc del c up to del m of Pm minus Pe by del naught equals to 0, where we cannot find the action of del naught and del c in it. The critical clearing angle is related to the equality of areas. It is termed as equal area criteria. It can be used to find out the utmost limit on the load which the system can acquire without crossing the stability limit. That means this method will help us to identify the changes to be made for an unstable system to make it stable by identifying the load angle. Since we have discussed, hence the condition for the transient state stability is given here. Del naught delta Pa del d delta is equals to 0. Here the area A1 represents the kinetic energy stored by the rotor during the acceleration, and the area A2 represents the kinetic energy given up by the rotor during the deceleration. The area under the curve Pa should be 0, which is possibly only when Pa has both accelerating and deaccelerating powers. For a part of the curve, Ps is greater than Pe, and for the other parts, Pe is greater than Ps. For a generation action, Ps is greater than Pe for the positive area, and A1 is greater than Ps for the negative areas A2 for stable region. Hence, the name equal-area criterion. The equal-area criterion is also used for determining the maximum limit on the load. Thank you.